Earth seems stable. Solid ground beneath our feet. Familiar sky overhead. We measure ourselves against the sun, its heat, its power. Yet the energy released in a single thunderstorm rivals what we see above. Lightning is hotter than the surface of the sun. A single bolt can reach temperatures around 30,000 Kelvin, several times hotter than the sun's photosphere. These flashes last only fractions of a second, yet they briefly create conditions more intense than the star that gives us life. The air itself becomes plasma, superheated gas torn apart into charged particles. Thunder is the sound of that air exploding outward. The sky above is more violent than it appears, but the ground beneath is equally unstable. Earth's magnetic field has flipped many times. Geological records show the planet's magnetic poles have reversed dozens of times throughout history, sometimes over relatively short periods. The last reversal occurred roughly 780,000 years ago. The next could happen at any time, or not for hundreds of thousands of years. The timing is irregular, unpredictable. During a reversal, the magnetic field weakens. It does not vanish entirely, but its protection diminishes. Radiation from space penetrates deeper into the atmosphere. Life has survived every past reversal. The biosphere adapts. Life adapts not only to changes above, but to conditions far below. Life exists kilometers beneath Earth's surface. Microbial ecosystems thrive deep underground, completely cut off from sunlight. They do not photosynthesize. They do not depend on the sun's energy. Instead, these organisms extract energy from chemical reactions, breaking down minerals, using heat from Earth's interior. They live in water trapped in porous rock, in cracks, in ancient aquifers sealed off for millions of years. Some of these microbes reproduce incredibly slowly. Their metabolism operates on geological timescales. A single generation might span centuries, yet they persist. Above ground, life depends on different forces. The moon stabilizes Earth's climate. Its gravity reduces chaotic changes in Earth's axial tilt. Without the moon, the tilt could vary wildly over millions of years, swinging from near zero to extreme angles. Such variations would cause dramatic climate shifts. Seasons would become unpredictable. Ice ages could arrive suddenly. Tropical zones could shift to polar latitudes and back. The moon acts as a stabilizer, anchoring Earth's orientation, allowing long-term climate stability. This stability may have been crucial for complex life to evolve. While the moon shapes conditions from above, material arrives from beyond. Earth is constantly bombarded by material from space. Tons of micrometeorite dust fall through Earth's atmosphere every day. Most of it burns up unnoticed, creating faint streaks of light too dim for human eyes to detect. This cosmic dust is ancient. Fragments from asteroids, remnants of comets, material left over from the solar system's formation. It drifts through space, intersects Earth's orbit, and falls. Some of this dust reaches the ground intact, accumulating in ice cores, in ocean sediments. Occasionally, larger fragments survive the descent. These become meteorites. They carry information about the early solar system, isotopes that reveal their age, minerals that formed in conditions unlike Earth. Most pass unnoticed. The bombardment is continuous. Yet Earth accumulates this material steadily, growing imperceptibly heavier year after year. The bombardment from space continues, but the heat it brings is nothing compared to what lies within. Earth's core is as hot as the sun's surface. Temperatures in the inner core reach roughly 5,400 degrees Celsius. This heat drives geological and magnetic processes. The core is iron, solid at the center, liquid in the outer layers. Pressure prevents the inner core from melting despite the temperature. The weight of the entire planet presses down. Heat flows outward from this core, rising through the mantle, reaching the surface. This flow powers the forces that reshape the planet. Continents are still moving. Tectonic plates shift centimeters per year, reshaping the planet over time. Oceans open and close on geological timescales. The Atlantic Ocean widens, the Pacific shrinks. India continues pushing into Asia, the Himalayas rise higher. This motion is continuous, invisible to human perception, but measurable with satellites. GPS reveals the drift, millimeters accumulating into kilometers. As plates collide, mountains grow. Mountains can grow taller while eroding. Uplift from plate collisions can exceed erosion rates. Some mountain ranges are rising even as they wear down. The Himalayas gain height each year. Rain washes material away. Glaciers carve valleys. Yet the tectonic forces pushing upward outpace the loss. The peaks continue climbing. This balance between destruction and creation shapes all landscapes. But the atmosphere itself has also been transformed. Earth once had no oxygen-rich atmosphere. Early Earth's air was toxic to modern life. Methane, carbon dioxide, nitrogen, but almost no oxygen. Oxygen accumulated only after photosynthetic organisms evolved. Cyanobacteria began releasing oxygen as waste. At first, the gas reacted with iron in the oceans, forming rust that settled to the sea floor. Banded iron formations preserve this history. Layers of red and grey stone. Evidence of an atmosphere being remade. Eventually, the oceans saturated. Oxygen began accumulating in the air. This transformation took billions of years. The atmosphere we breathe is a biological product, created by life, sustained by life. Even the water we depend on may predate the planet itself. Most of Earth's water may be older than the planet. Hydrogen isotopes suggest some water formed before Earth itself. It may have been inherited from early solar system material. Water arrived through impacts. Comets and asteroids carried ice. Volatile compounds locked in rock, delivered during the violent early bombardment. Some of this water has been here since the beginning, cycling through oceans, atmosphere, and rock. Never destroyed, only transformed. But the atmosphere does lose material. Earth's atmosphere leaks into space. Light gases like hydrogen slowly escape Earth's gravity. This loss has occurred for billions of years. High in the atmosphere, solar radiation breaks apart water molecules. Hydrogen escapes, oxygen remains. The process is slow, but relentless. Over geological time, Earth has lost hydrogen. The escape continues today, invisible, constant. Meanwhile, another slow change unfolds. Earth's rotation is slowing. Tidal interactions with the moon lengthen Earth's day. Ancient days were much shorter. The moon pulls on Earth's oceans, creating tidal bulges that drag against the sea floor. The planet spins more slowly. The moon drifts farther away. Days were once only about 18 hours long. Fossil patterns indicate faster rotation. The change is imperceptible in human lifetimes, but cumulative over deep time. The slowing continues. But rotation is not the only orbital change. Earth's axial tilt changes over time. These shifts influence long-term climate cycles. Ice ages are partly driven by orbital variations. The tilt wobbles between roughly 22 and 24.5 degrees. The cycle takes about 41,000 years. When the tilt is greater, seasons become more extreme. Hotter summers, colder winters. When the tilt is smaller, seasonal differences diminish. These variations combine with other orbital changes: the shape of Earth's orbit, the direction of the tilt. Together, they create patterns that trigger ice ages. Ice ages are the norm, not the exception. Warm periods like today are relatively rare in Earth's history. Most of the past was colder. For much of the last few million years, ice sheets covered vast regions. Glaciers reached down from the poles. Sea levels dropped. Land bridges appeared between continents. The warm interglacial we live in now is unusual. These climate swings are moderated by a massive buffer. Earth's oceans regulate global temperature. They absorb and redistribute enormous amounts of heat. Without them, climate extremes would be severe. Water has high heat capacity. It takes enormous energy to warm or cool. The oceans store heat during summer, release it during winter. Coastal regions experience milder climates than continental interiors. The ocean stabilizes nearby temperatures. Without this buffering, day-night and seasonal swings would be far more extreme. The oceans do not sit still. Ocean currents act like planetary conveyor belts. They transport heat across the globe. Disruptions can rapidly alter climate. Warm water flows from the tropics toward the poles. Cold water sinks and returns along the ocean floor. This circulation redistributes heat, stays warmer than it otherwise would. The Gulf Stream carries tropical warmth northward. If these currents weaken or stop, regional climates shift dramatically. Past disruptions triggered abrupt cooling events, temperature changes of several degrees within decades. The ocean circulation is sensitive to changes in salinity and temperature. These oceans contain depths that exceed the highest mountains. Earth's deepest ocean trench exceeds Mount Everest in depth. The Mariana Trench plunges deeper than Everest is tall. Most of it remains unexplored. The trench reaches nearly 11 kilometers down. Everest rises roughly 8.5 kilometers above sea level. If Everest were placed in the Mariana Trench, water would still cover its peak by more than 2 kilometers. At such depths, conditions become extreme. Pressure at ocean depths can crush steel. At extreme depths, pressure reaches over 1,000 times atmospheric pressure. Specialized life adapts to these conditions. The weight of the water above presses down with immense force. Ordinary materials collapse. Yet organisms thrive there. Their cells contain no air pockets. Their proteins fold differently. They evolved under crushing weight. Much of this deep ocean remains invisible from the surface, but beneath it lies even more hidden activity. Earth has more volcanoes underwater than on land. Most volcanic activity occurs beneath oceans. New crust forms continuously at mid-ocean ridges. These ridges stretch for tens of thousands of kilometers. Magma rises from the mantle, cools, solidifies, creating new seafloor. This process is called seafloor spreading. It pushes continents apart. The Atlantic grows wider. The Americas drift from Europe and Africa, year by year. These mid-ocean ridges are volcanic. Magma pushes upward from the mantle, creating new seafloor. But this is only the most recent volcanic activity. Throughout history, volcanoes have shaped more than the surface. They built the air itself. Volcanoes helped create Earth's atmosphere. Early volcanic outgassing released water vapor and gases. Before life produced oxygen, volcanoes filled the air. Carbon dioxide, sulfur compounds, nitrogen, water vapor that eventually condensed into oceans. The atmosphere we know is partly volcanic in origin. Most volcanoes are small, localized eruptions that affect limited areas. But some are not. Supervolcanoes exist beneath continents. Their eruptions are rare but massive. Past events reshaped ecosystems worldwide. Yellowstone sits atop one. A supervolcano does not form a mountain. Instead, it creates a caldera, a collapsed crater tens of kilometers across. Beneath it, a reservoir of magma accumulates. When a supervolcano erupts, it releases hundreds of cubic kilometers of material. Ash spreads across continents, blocking sunlight, cooling global temperatures. The last major eruption at Yellowstone occurred roughly 640,000 years ago. These events are infrequent, but their effects are profound. All of this volcanic power rises through a surprisingly thin layer. Earth's crust is thinner than an apple's skin proportionally. Relative to Earth's size, the crust is extremely thin. The planet is mostly mantle and core. Continental crust averages about 30 to 50 kilometers thick. Oceanic crust is even thinner, only about 7 kilometers. Beneath lies the mantle, nearly 3,000 kilometers deep. The mantle is not liquid, but it is not entirely solid either. Earth's mantle flows slowly, like thick liquid. Over millions of years, solid rock behaves plastically. This motion drives plate tectonics. The mantle convects. Hot material rises, cool material sinks, like water heating in a pot, but infinitely slower. This circulation carries heat from the core to the surface. It powers the movement of continents, the opening and closing of oceans, everything that reshapes the surface. At the very center, changes continue. Earth's inner core may be growing. As the planet cools, the solid inner core slowly expands. This influences the magnetic field. The core cools extremely slowly. Heat escapes at a rate measured in fractions of a degree per million years. As it cools, iron crystallizes, adding to the solid inner core. The process will continue for billions of years. The magnetic field generated by the core is not decorative. Earth's magnetic field protects life from radiation. It deflects charged solar particles. Without it, atmospheric loss would increase. The field extends far into space, creating a magnetosphere around the planet. Solar wind flows around this invisible shield. Most particles are diverted. Some particles do penetrate near the poles, creating auroras, the northern and southern lights. visible evidence of the magnetic field at work. But the sun's activity varies. Magnetic storms can disrupt technology. Solar activity interacts with Earth's magnetosphere. Strong storms can damage satellites and grids. During solar storms, charged particles intensify. They interfere with radio signals, disrupt GPS, induce currents in power lines. The most powerful recorded storm occurred in 1859, the Carrington event. Telegraph systems failed. Some caught fire. A similar event today would affect far more infrastructure. The magnetic field is our protection, but it is not constant. Earth's poles wander over time. Magnetic and geographic poles shift due to internal dynamics. They are not fixed points. The magnetic North Pole moves tens of kilometers per year. Its position changes as currents in the outer core shift. Throughout the 20th century, it migrated across the Canadian Arctic. Now it moves towards Siberia. These shifts are tracked by navigational systems. Maps must be updated. The wandering is normal, part of the planet's ongoing dynamic processes. Despite all these changes, the magnetic field reversals, the wandering poles, life persists. Earth has survived multiple mass extinctions. At least 5 major extinction events reshaped life. Each reset biodiversity dramatically. The most severe occurred roughly 250 million years ago, the Permian-Triassic extinction. It killed more than 90% of marine species, most land vertebrates. The causes varied: volcanic eruptions, asteroid impacts, climate shifts, sometimes combinations of factors. Each event left the planet transformed. Yet life did not end. Life rebounded after every extinction. Evolution filled emptied niches repeatedly. Recovery often took millions of years. After the asteroid that killed the dinosaurs, small mammals diversified. They occupied ecological roles left vacant. New forms emerged. Complexity rebuilt itself. But recovery was not always straightforward. Some extinctions pushed the planet to extreme states. Earth was once almost entirely frozen. Snowball Earth episodes covered oceans in ice. Life survived in refuges. These events occurred more than 600 million years ago. Ice extended from the poles to the equator. Reflective ice amplified cooling. Temperatures plummeted. Yet life endured. Possibly near volcanic vents, in pockets of open water, beneath the ice where sunlight still penetrated. Eventually, volcanic carbon dioxide accumulated. The greenhouse effect strengthened. Ice melted rapidly. The planet swung from frozen to hot. At other times, the opposite occurred. Earth's atmosphere once trapped far more heat. Ancient greenhouse conditions supported tropical poles. Carbon dioxide levels were much higher. 50 million years ago, palm trees grew in Antarctica. Crocodiles lived in the Arctic. No permanent ice existed at either pole. The planet was fundamentally warmer. These swings between hot and cold reveal something critical. Earth's climate system has tipping points. Small changes can trigger large effects. Feedback loops amplify shifts. Ice reflects sunlight. Less ice means more heat absorbed. More heat melts more ice. The cycle accelerates. Carbon dioxide warms the planet. Warming releases more carbon from permafrost and oceans. More carbon causes more warming. Positive feedback. These processes operate in both directions. They can lock the planet into stable states, hot, cold, or somewhere between. And life itself plays a role in these shifts. Earth's biosphere alters the planet itself. Life changes atmospheric chemistry. Biology and geology are linked. Photosynthetic organisms created the oxygen atmosphere. Plants stabilize soil, prevent erosion. Coral reefs build limestone structures. Microbes drive chemical cycles. The planet and its life cannot be separated. They shape each other. Earth is not a stage on which life acts. It is a system where life is part of the machinery. Life's influence on the planet extends to weather itself. Forests influence rainfall patterns. Large forests recycle moisture into the atmosphere. Deforestation can reduce regional rainfall. Trees release water vapor through their leaves. This process is called transpiration. In tropical rainforests, the effect is massive. Much of the rain that falls is water the forest itself released. When forests are removed, less moisture enters the air. Clouds form less frequently. Rainfall decreases. The climate dries. Yet even in the driest places, life waits. Deserts can bloom rapidly. Dormant seeds activate after rare rains. Entire ecosystems can appear briefly. Seeds lie buried for years, sometimes decades. When water finally arrives, they germinate within days. Flowers blanket landscapes that were bare. The bloom lasts only weeks. Seeds are produced quickly. Then the plants die. New seeds enter dormancy, waiting for the next rain. Beneath all these landscapes, whether forest or desert, something invisible sustains everything. Earth's soil is alive. It contains vast microbial networks. These regulate nutrients and carbon. A single handful of soil holds billions of microorganisms. Bacteria, fungi, archaea. They decompose organic matter, release nutrients plants need. Without soil microbes, dead material would accumulate. Nutrients would remain locked away. Plants could not grow. The cycle would break. These microbes are not exceptional. Most life on Earth is microbial. Microbes dominate biomass and diversity. Complex life is a minority. The largest fraction of Earth's biomass consists of bacteria. They live everywhere. In oceans, deep underground, high in the atmosphere, inside other organisms. They outnumber all plants and animals combined, by mass, by cell count, by genetic diversity. Visible life is the exception. Microbial life is the rule. And their influence extends far beyond their size. Microbes shape global chemistry. They drive nitrogen and carbon cycles. Life depends on invisible processes. Nitrogen in the atmosphere is inert. Plants cannot use it directly. Bacteria convert it into usable forms. This process is called nitrogen fixation. Without these bacteria, most ecosystems would collapse. Plants could not grow. Animals would have nothing to eat. The foundation of the food web depends on microbial chemistry. Some microbes endure conditions beyond Earth. Some organisms can survive in space briefly. Certain microbes tolerate vacuum and radiation. Life can endure extreme environments. Experiments have exposed bacteria to space conditions. Some survived. Protected by dormancy, thick cell walls, repair mechanisms for damaged DNA. They cannot reproduce in space, but they can survive long enough to potentially travel between worlds. If protected inside rock, shielded from radiation, Back on Earth, life depends on layers that shield it. Earth's atmosphere has layers with distinct roles. Each layer absorbs different radiation. Life depends on this structure. The troposphere is where weather occurs. The stratosphere contains the ozone layer. The mesosphere burns up meteors. The thermosphere absorbs high-energy radiation. Each layer filters something dangerous. Together, they create conditions where life can exist. Without this layered protection, Earth's surface would be uninhabitable. One layer in particular made life on land possible. The ozone layer, formed after oxygen rose. It blocks harmful ultraviolet radiation. This enabled life on land. Ozone is a form of oxygen. 3 oxygen atoms bonded together. It forms naturally in the stratosphere when ultraviolet light strikes oxygen molecules. Before oxygen accumulated in the atmosphere, no ozone layer existed. Ultraviolet radiation reached the surface unfiltered. Life remained underwater, protected by water itself. Only after photosynthetic organisms produced enough oxygen did the ozone layer form. This took billions of years. Once established, it allowed organisms to colonize land. A biological product protecting biological expansion. Today, we rarely see the sky as it once appeared. Earth's night sky was once far darker. Light pollution is a recent phenomenon. Most humans have never seen a pristine sky. Cities glow. Streetlights scatter into the atmosphere. The scattered light obscures stars. The Milky Way becomes invisible. A century ago, anyone could look up and see thousands of stars. Now, in many places, only a few dozen are visible. The sky has not changed. Our view of it has. The planet itself has subtle variations we rarely notice. Earth's gravity is not uniform. Density variations affect local gravity. Satellites detect subtle differences. Mountains create stronger gravitational pull. They contain more mass than surrounding regions. Ocean trenches create weaker pull, less mass below. These variations are tiny, but measurable. Gravity mapping satellites orbit Earth, detecting changes as small as 1 part in a million. The planet's shape also deviates from perfect. Earth's shape is slightly squashed. Rotation causes equatorial bulging. It is not a perfect sphere. The equator bulges outward by about 21 kilometers compared to the poles. Centrifugal force from rotation pushes material outward. The planet is an oblate spheroid. This shape affects everything. Satellite orbits, GPS calculations, even the definition of sea level. The ocean surface follows the geoid, a shape defined by gravity. Earth's path through space also deviates from perfection. Earth's orbit is slightly elliptical. Distance from the Sun varies annually. This does not cause seasons. The orbit brings Earth closest to the Sun in January, farthest in July. Yet January is winter in the northern hemisphere. The distance variation is too small to matter. Seasons are caused by axial tilt. The tilt changes sunlight angles. Distance plays a minor role. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight. Days are longer, temperatures rise. Summer. When tilted away, sunlight strikes at a shallow angle. Days are shorter, temperatures fall. Winter. Throughout these seasons, Regardless of Earth's position, radiation arrives from beyond. Earth receives constant cosmic radiation. Most is blocked by atmosphere and magnetism. Some particles reach the surface. Cosmic rays are high-energy particles, protons mostly, accelerated to nearly light speed by distant events. Supernovae, black holes. They rain down continuously, colliding with atoms in the upper atmosphere, creating showers of secondary particles. Some reach the ground, pass through us. The atmosphere absorbs most of this radiation. At sea level, exposure is minimal. At high altitudes, it increases. But Earth's layered defenses protect life below. The atmosphere does more than block radiation. It also creates light of its own. Earth's atmosphere glows faintly at night. Airglow comes from chemical reactions. It is invisible to most people. High in the atmosphere, atoms and molecules absorb energy during the day, from sunlight, from cosmic rays. At night, they release this energy as faint light. Oxygen emits green. Sodium emits yellow. The glow is too dim for human eyes to detect without instruments, but cameras can capture it. A permanent aurora of sorts. Proof that the atmosphere is never truly dark. While the atmosphere records processes in light, the ground records them in stone. Earth's crust stores ancient magnetic records. Rocks preserve past field orientations. This revealed magnetic reversals. When lava cools, iron minerals align with the magnetic field. They lock into place as the rock solidifies. The orientation is preserved. A snapshot of the field at that moment. By studying rocks of different ages, scientists mapped when reversals occurred. The pattern became clear. The field has flipped dozens of times, written in stone across the planet. Most of Earth's geology lies hidden beneath water. Earth's oceans contain most habitable volume. Liquid water environments dominate. Land is a small fraction. The oceans hold roughly 97% of Earth's water. They cover 70% of the surface, and they extend to depths exceeding 10 kilometers. The volume is vast. Most of Earth's living space is underwater. The deep ocean offers more room than all terrestrial environments combined. Yet much remains unexplored. We know more about the surface of Mars than the deep seafloor. Life occupies not just the surface and ocean, but the space above. Earth's biosphere extends into the atmosphere. Microbes are found kilometers high. Life occupies more space than expected. Bacteria float in clouds, carried upward by winds. Some survive at altitudes where temperatures drop far below freezing, where pressure is a fraction of sea level. They do not thrive there, but they persist, dormant, waiting to descend. The atmosphere is not sterile. The landscapes below have changed profoundly over time. Earth's deserts were once seas. Geology preserves ancient shorelines. Environments change dramatically. The Sahara was green 6,000 years ago. Rivers flowed. Lakes filled valleys. Fossils of hippos and crocodiles lie in what is now barren sand. The climate shifted. Further back, deserts were oceans. Marine fossils are found far from any coast. Mountains contain limestone, formed from ancient coral reefs. The rock beneath our feet was once seafloor, or volcanic plains, or buried deep. Nothing stays where it began. Earth's surface is constantly recycled. Crust is created and destroyed. Nothing is permanent. Oceanic crust forms at mid-ocean ridges. It spreads outward, eventually reaches a subduction zone, sinks back into the mantle. The oldest seafloor is only about 200 million years old. Everything older has been consumed. Continents endure longer, but they too erode and reform. Despite this constant change, traces of the past remain. Earth's history is written in isotopes. Atomic ratios reveal age and origin. Time leaves chemical fingerprints. Radioactive elements decay at known rates. Parent isotopes become daughter isotopes. By measuring both, scientists determine when a rock formed, or when an organism died. Isotopes also reveal temperature, ancient ocean chemistry. Every rock carries a record. The planet documents its own history in atoms.
These atomic records reveal atmospheres very different from today. Earth's atmosphere once had orange skies. Methane hazes altered early light. The sky did not always appear blue. Before oxygen dominated, methane was abundant. Organic haze particles formed in the upper atmosphere. They scattered light differently than today's nitrogen and oxygen. The sky would have appeared orange or brown, similar to Saturn's moon Titan. These changes in atmosphere accompanied dramatic shifts in temperature. Earth's temperature has swung wildly. Climate stability is recent. Extremes dominated the past. Ice ages alternated with hothouse periods. Frozen oceans gave way to tropical poles. The planet oscillated between states. Current stability is unusual in Earth's long history. Part of what shapes Earth's environment is its gravitational influence. Earth's mass attracts nearby debris. Gravitational focusing increases impacts. Larger bodies collide more often. A larger planet sweeps up more material from surrounding space. Its gravity pulls in asteroids and comets that would otherwise miss. This is why Earth has been struck more frequently than smaller bodies like the Moon per unit surface area. Gravity also shapes the patterns in the air. Earth's rotation affects weather. Coriolis forces shape winds. Storms owe their spin to rotation. Moving air deflects to the right in the northern hemisphere, to the left in the southern hemisphere. This creates rotating weather systems. Hurricanes spin counterclockwise in the north, clockwise in the south. Without rotation, winds would flow directly from high to low pressure. No spirals, no cyclones. Weather would be fundamentally different. Deep beneath these weather patterns, another process generates protection. Earth's interior is electrically conductive. Flowing metals generate magnetism. This powers the magnetic field. The outer core is liquid iron and nickel. It flows in complex patterns, driven by heat from below. Rotation organizes the flow. Moving conductive fluid creates electric currents. These currents generate magnetic fields. The process is called the geodynamo. It has operated for billions of years, protecting the planet from space. The magnetic field has protected Earth for billions of years, allowing water to persist. Earth's surface water cycles endlessly. Evaporation and precipitation redistribute heat. The cycle stabilizes climate. Water evaporates from oceans, rises into the atmosphere as vapor, forms clouds, falls as rain, returns to the ocean through rivers and groundwater. This cycle moves enormous amounts of energy. When water evaporates, it absorbs heat. When it condenses, it releases that heat. The process redistributes warmth from the tropics toward the poles. Without this cycle, temperature extremes would be far greater. The oceans would heat endlessly. The land would bake. Water circulation moderates both. Another cycle operates on far longer timescales. Earth's carbon cycle spans millions of years. Carbon moves between rock, ocean, air, and life. Imbalances alter climate. Volcanoes release carbon dioxide. Plants and phytoplankton absorb it. When organisms die, some carbon is buried, eventually becoming limestone or fossil fuels. Subduction carries carbon-rich rocks deep into the mantle. There, it melts, returning to the surface through volcanic eruptions. The loop closes over geological time. This carbon cycle maintains balance. Too much volcanic activity raises atmospheric carbon. Temperatures rise. Weathering increases. More carbon is pulled from the air and locked into rock. The system self-regulates, slowly. The atmosphere itself has evolved dramatically. Earth's atmosphere once lacked nitrogen dominance. Gas composition evolved over time. Today's mix is not original. Nitrogen now makes up 78% of the atmosphere. But early Earth's air contained far less. It accumulated gradually over billions of years, released by volcanic outgassing and biological processes. Chemically inert, it did not react away like other gases. The oceans play a critical role in atmospheric chemistry. Earth's oceans absorb carbon dioxide. They buffer atmospheric changes. Acidification alters marine life. When carbon dioxide dissolves in seawater, it forms carbonic acid. This lowers the ocean's pH. Marine organisms that build shells struggle. Corals, mollusks, certain plankton, their shells are made of calcium carbonate. Acidic water dissolves it. The ocean has absorbed much of the carbon dioxide released by human activity. This has slowed atmospheric warming, but it has altered ocean chemistry rapidly. The solid ground itself floats on something denser. Earth's continents float on denser mantle. They are buoyant crustal blocks. This enables tectonics. Continental crust is less dense than oceanic crust, and both are less dense than the mantle beneath. Continents rise higher. Mountains have deep roots extending into the mantle. The crust floats at equilibrium. On this floating crust, life has adapted to gravity. Earth's gravity shapes living forms. Biology adapts to constant force. Structure reflects physics. Bones must support weight. Trees have thick trunks. Insects remain small because their exoskeletons cannot support large mass. Life is shaped by its physical environment. And that environment depends on a narrow temperature range. Earth's surface temperature allows liquid water. This narrow range is crucial. Small changes matter. Water remains liquid between 0 and 100 degrees Celsius. Earth's average surface temperature is about 15 degrees, well within this range. If the planet were slightly closer to the sun, water would evaporate. Slightly farther, and it would freeze. The habitable zone is narrow. This narrow habitable zone is where Earth has existed for most of its history. Earth's age is about 4.54 billion years. Radiometric dating confirms this. The planet formed early in solar history. Certain isotopes decay at known rates. By measuring parent and daughter isotopes in ancient rocks, scientists determine when they solidified. The oldest Earth rocks are about 4 billion years old. But meteorites that formed alongside Earth are older. They preserve the solar system's formation age. That formation was not gentle. Earth formed through violent collisions. Accretion involved constant impacts. Calm came later. Dust grains stuck together, forming pebbles, then boulders. Planetesimals collided and merged. Each impact added mass, released heat. The early Earth was molten. Bombardment kept the surface liquid. Heavier elements sank toward the center. Iron descended to form the core. Lighter materials floated upward. One collision reshaped everything. Earth's moon likely formed from a massive impact. Debris coalesced into the moon. This event reshaped Earth. A Mars-sized object struck the young Earth. The impact vaporized rock, ejected enormous amounts of material into orbit. Some fell back, some escaped. The rest formed a disk around Earth. Within that disk, debris clumped together. Gravity pulled it into a sphere. The moon. The impact melted Earth's surface again. It also tilted Earth's axis, creating the obliquity that gives us seasons. After the moon formed, bombardment continued for hundreds of millions of years. Earth's early atmosphere came from impacts. Volatiles arrived via collisions. External material shaped conditions. Comets and asteroids carried water, carbon dioxide, nitrogen. These compounds were locked in ice and rock. Impacts delivered them to the surface. Without this delivery, Earth might have remained dry. The oceans are partly extraterrestrial. The atmosphere, too. Once oceans formed, they began influencing the air. Earth's oceans influence atmospheric oxygen. Marine life produces most oxygen. Land plants came later. Phytoplankton in the ocean photosynthesize. They release oxygen as a byproduct. The ocean's biological productivity drives much of the atmosphere's oxygen content. More than half. When ocean circulation changes, oxygen production shifts. Dead zones form where oxygen is depleted. The balance is fragile. Life also shapes how much sunlight the planet reflects. Earth's biosphere modifies reflectivity. Vegetation alters albedo. This affects temperature. Forests are dark. They absorb sunlight. Snow and ice are bright. They reflect it. When vegetation replaces ice, the surface warms. Deserts reflect more light than forests. Oceans absorb more than land. The distribution of these surfaces matters. It influences global temperature. And that distribution constantly shifts. Earth's landmass distribution affects circulation. Continents redirect winds and currents. Geography shapes climate. When continents cluster near the poles, ice accumulates. When they cluster at the equator, ocean currents flow freely around the poles. Heat distributes differently. The position of land masses determines whether Earth enters an ice age or remains warm. Millions of years ago, when continents were arranged differently, climates were different. Ocean currents followed other paths. Wind patterns shifted. The planet responded to its changing geography.
Geography shapes climate, and climate reshapes geography. Earth's glaciers sculpt landscapes. Ice reshapes terrain. Valleys and fjords remain as evidence. Glaciers advance when snowfall exceeds melting. Ice accumulates, compresses, begins to flow under its own weight. Moving ice carves rock. It plucks boulders from bedrock, grinds them into smaller pieces. The debris acts like sandpaper, polishing valleys into U-shapes. When glaciers retreat, they leave behind moraines, piles of debris marking their former extent. Kettle lakes form where ice blocks melted. The landscape remembers the ice. Yet not all of Earth's history involves such dramatic change. Earth's history includes long, stable eras. Not all change is catastrophic. Stability allows complexity. Between major events, conditions often remain steady for millions of years. Ecosystems mature. Species diversify. Complex interactions develop. Stability is not stagnation. Evolution continues. But the environmental backdrop remains relatively constant. These periods allow life to develop elaborate adaptations. Part of this stability comes from internal regulation. Earth's biosphere has self-regulating tendencies. Feedback loops can stabilize systems. They are not perfect. When carbon dioxide rises, plants grow faster. More carbon is absorbed. When temperatures rise, weathering increases. More carbon is locked into rock. These feedbacks dampen changes, preventing runaway effects. To a point. The regulation has limits. Push too hard, and the system shifts. Earth's future climate depends on multiple variables. Orbital, geological, and biological factors interact. No single cause dominates. The planet's tilt wobbles. Its orbit shifts. Volcanic activity varies. Continental positions change. Life evolves. All of these influence climate. Predicting the far future is difficult. Too many variables interact over timescales too long to model precisely. But some trends are clear. The oceans will not last forever. Long-term heating increases evaporation. Planetary futures change. The sun is gradually brightening. As it ages, its luminosity increases. In a billion years, it will be about 10% brighter than today. Earth's surface will warm. Higher temperatures increase evaporation. Water vapor is a greenhouse gas. More vapor traps more heat. A feedback loop accelerates warming. Eventually, the oceans will evaporate. Water vapor will rise high into the atmosphere. Ultraviolet radiation will split it apart. Hydrogen will escape to space. Oxygen will remain, binding to rocks. The water will be lost. This means Earth's habitability is temporary. Planetary conditions evolve. Stability has limits. Life has existed for billions of years, but it will not last indefinitely. The conditions that allow liquid water will eventually disappear. The window is closing slowly. But Earth does not evolve in isolation. Earth exists within a dynamic solar system. External forces influence conditions. Isolation is an illusion. Asteroids pass nearby. Solar radiation varies. Gravitational tugs from Jupiter and Saturn alter Earth's orbit subtly. The Moon's orbit changes. These influences are small, but over geological time they accumulate. Earth is part of a larger system, not a closed world. What happens elsewhere affects what happens here. The solar system shapes Earth's fate. These external influences operate across timescales almost impossible to grasp. Earth's environment reflects deep time. Present conditions are a snapshot. The past was different. What we see today is not representative of Earth's full history. The oxygen-rich atmosphere, the moderate temperatures, the stable continents.
These conditions have not always existed. They will not always exist. Earth's environment is temporary, a moment in a much longer story. And that story continues to unfold. Earth's future includes continental rearrangement. New supercontinents will form. Geography will change. The continents are still drifting. In 250 million years, they may merge again, forming a new Pangea. Oceans will close. New oceans will open. Mountain ranges will rise where none exist today. Coastlines will shift. Climates will redistribute. The map of Earth will be unrecognizable. Life will adjust to these changes. Earth's biosphere adapts but has limits. Change beyond thresholds causes collapse. Recovery takes time. Evolution is powerful. Organisms adapt to new conditions. Ecosystems reorganize. But adaptation requires time. Rapid changes outpace evolution. Species cannot adapt fast enough. Extinctions occur. Complexity is lost. Recovery is possible, but it takes millions of years. The biosphere has limits. Push beyond them, and systems collapse. Yet despite collapses and changes, processes continue. Earth's story is ongoing. Processes continue today. Nothing is finished. Continents still drift. Volcanoes still erupt. The core still generates a magnetic field. Water still cycles. Evolution still operates. Species still go extinct. New ones still emerge. The planet is not static. It never was. Earth is shaped by internal and external forces. Geology and space both matter. Balance defines outcomes. Heat from the core drives tectonics. Impacts from space deliver materials. The sun provides energy. The moon stabilizes the tilt. Internal processes reshape the surface. External forces influence climate. Neither dominates alone. Both shape what Earth becomes. And what it becomes is never certain. Earth's stability is not guaranteed. Conditions can shift. History shows vulnerability. Ice ages arrived. Hothouse periods dominated. Mass extinctions occurred. Magnetic fields weakened. The planet has survived. But survival does not mean immunity. Stability is contingent, not inevitable. Yet from instability, order has emerged. Earth's complexity emerges from simple rules. Physics governs outcomes. Complexity accumulates. Gravity pulls matter together. Heat drives convection. Chemistry allows reactions. These simple principles interact. From them, continents form. Oceans circulate. Atmospheres evolve. Life emerges. None of these outcomes were predetermined. They arose from physical laws operating over billions of years. Complexity built upon itself. Simple rules created intricate systems. And those systems continue operating. The same physics that formed Earth still governs it. The future will emerge from the same principles. Simple, relentless, transformative. Those transformations require specific conditions. Earth's life depends on chemistry and energy. Both must align. Neither alone is sufficient. Chemistry provides the mechanisms. Carbon bonds form complex molecules. Water dissolves and transports. Proteins catalyze reactions. But chemistry needs energy to operate. Sunlight drives photosynthesis. Chemical gradients power metabolism. Heat from hydrothermal vents sustains deep-sea ecosystems. Without energy, chemistry remains static. Without chemistry, energy dissipates uselessly. Life requires both, aligned precisely. This alignment may not be unique. Earth's uniqueness may be temporary. Other worlds change too. Comparisons evolve. Mars once had liquid water. Venus may have had oceans. Moons of Jupiter and Saturn harbor subsurface seas. What seems unique today might become common tomorrow. As we learn more, Earth's distinctiveness may fade or sharpen. The answer is not yet clear. What is clear is that understanding Earth helps us understand change itself. Earth's past holds lessons for the future. Patterns repeat under new conditions. Understanding matters. Ice ages have come before. They will come again. Mass extinctions happened. They could happen again. By studying past changes, we learn how systems respond, how quickly they shift, how slowly they recover. The past is a guide, but the present is unusual. Earth's present is unusually calm. Chaos dominated much of history. Calm enabled civilization. For most of Earth's existence, conditions were more extreme, more volatile. The current interglacial is stable. Temperatures moderate, sea levels steady. This stability is recent and temporary. Within this calm, everything connects. Earth's systems are interconnected. Change propagates across domains. Nothing acts alone. Oceans influence atmosphere. Atmosphere affects ice. Ice changes albedo. Albedo alters temperature. Volcanoes emit gases. Gases trap heat. Heat drives weathering. Weathering removes gases. Every part affects every other part. The system is coupled. Change in one domain ripples through the rest. And this system exists on a timeline far longer than our own. Earth's story is not human-centered. Life existed long before humans. It will continue after. For 3.5 billion years, life persisted without us. Microbes dominated. Complex organisms arose. Dinosaurs ruled for hundreds of millions of years. Humans appeared only recently. A few 100,000 years. A blink in geological time. The planet does not revolve around us. We are participants in a story much larger and older than our species. Earth is a moment in cosmic time. Temporary conditions allow complexity. Nothing lasts forever. The planet formed. It evolved. It will continue evolving. Eventually, conditions will shift beyond habitability. The oceans will evaporate. The sun will expand. In billions of years, Earth will be consumed or scorched into a lifeless rock. But for now, it exists. Dynamic, complex, changing, a world in motion, shaped by time, home to life. For a moment in cosmic time.